Hey, I'm coding a bot to beat a strategy game, and I'm documenting it so we can learn together along the way. This part of the series is on computer vision. By the end of this video, you'll be able to scrape the important elements out of an image like this into simple variables for the rest of your app's code to use. In a future video, we'll send those variables to an AI model so it can make the best in-game decisions possible to win the game. If you're new here, my name is Devin, and this channel is for coders interested in gaming, hacking, and AI. Let's get into it. There are several approaches to extracting information out of a game. Computers don't have eyes like we do, so they can't just visually see what's happening in the game. But without this information, the AI can't make decisions. In a previous video, I showed how to extract text out of an image. On this screen, the important text elements could be the round number, how much time I have left, how much health I have, and on this other screen, there are many more text elements, such as the characters that are available to purchase from the shop, how much gold I have, what level I am, how much experience I have, etc. Unfortunately, there are some data elements that the AI needs which are not available as text. For example, this little fire icon tells me if I'm on a win or loss streak, and that affects how much bonus gold I get after each round. So I may want to intentionally keep losing if I'm already on a loss streak, or I may want to spend all of my gold to keep winning if I'm on a win streak. But because this is an image with no text, I can't use the techniques from the previous video. In addition, on this screen, there are icons which represent the item I will receive if I pick that unit. But this screen is more complicated because, as you saw previously, the units with their items are rotating around in a circle. So we'll use two different techniques for scraping these images. One for this fire icon, because it's in a static position, we always know the X and Y coordinates. We just need to determine if it's blue, red, or gray. And a separate technique for these items because they're moving around the screen and we don't know their location. Now, the actual 3D model of the character would be useful to scrape so that we know which character we're selecting. But that's much more difficult because the 3D model is animated. So as it walks around in a circle, it's turning and also animating footsteps, whereas these items are just a static image. Although we could try to analyze the 3D model, we're going to use the easiest technique for each approach. And in this case, I can instead click on this eyeball, which will pop up an overlay like this on the side of the screen. And from this overlay, I can just read the character's name using the text recognition algorithm I showed in the previous video. So there's no reason to code a complicated algorithm to analyze the 3D model if we don't need to. Now, one other approach that is common is to actually read the memory of the game while it's executing, because in the game's RAM, it knows what characters it's rendering on the screen and where. And so if we could find those variables, we could get the data that way. I've chosen not to use this approach simply because I know Riot has anti-cheat mechanisms in their code. So each time they patch the game, the memory locations are going to change, and I don't want to have to recode my AI constantly. But I know the visuals are unlikely to change because those are the most important for the player experience. And scraping the image is not incredibly difficult as long as we're not dealing with 3D models. So let's start the code that can scrape this fire icon out of the game. Here I've opened Visual Studio Code, and I have some boilerplate code pasted in. This is actually the project I started in the previous video. So as a reminder, Lodash has some useful utility functions that are common in any JavaScript program. OpenCV is for computer vision, so it will help us analyze images. And TensorFlow is for neural networks. However, it also has a lot of matrix math formulas, and images are essentially matrices of colors. So some of these math formulas will be useful. FS, Path, and OS are just utility libraries built into the Node.js platform that will help me access files off my hard drive. And in this case, I've extracted screenshots out of my gameplay so that I can quickly make changes to my code and retest without launching a brand new game and playing to that specific screen. For these imports to work, Lodash, OpenCV, and TensorFlow, I had to open the terminal and I had to type npm install and the package name. Those packages are hosted on the npm.js website, and the npm install command modifies my package JSON to add that package as a dependency along with a version number. A package is essentially a library of code that I can use. Those packages are downloaded into this node modules folder inside of my project, and you'll notice hundreds of packages even though I only picked a few, and that's because the packages I installed may depend on other packages. But for example, under the @u4, I can see the OpenCV Node.js that I imported. So here's the code. I don't need to read any of that code. When I type the import command, JavaScript knows to find the code and allow me to reference it. This way, I don't have to reinvent the wheel by coding my own computer vision algorithms. I can use the ones from this open source library that someone else has already coded for me. Okay, let's get started coding. I'm going to make a function called rImagesSimilar. And you could call this whatever you want. And it's going to return a Boolean, meaning true or false. The purpose of this function will be to take one of these two icons, the blue or red streak, and compare it to this image to see if it's a match. However, I'm not going to compare the entire image. Instead, I will crop just this portion of the image and compare it. So I need to pass the images into this function. I'll call it image A, and it will be of type computer vision matrix, which again, an image can be represented as a matrix. I'll have a second image, and I'll also pass in a parameter called threshold, which is essentially the percentage match that I require to consider the images similar. This will allow me to fine-tune my results so that if the algorithm is not working, I can increase or decrease the percentage of what is considered a match. The algorithm I'm going to use for the rImagesSimilar function is called mean squared error. And let me explain the math behind how that works before I code it. Let's pretend I have 3 images. Each image could be represented as a matrix of colors. So these images have 2 pixels wide and 3 pixels tall. And I'm going to open up a program I like called Color Cop to explain how pixels are represented in the computer. So this first pixel on the top left corner of the first image is 255,0,0. The first number is the red, the second is the green, and the third is the blue. So I have full intensity on the red channel and no intensity at all on the green or the blue. 255 is the maximum number, and that's because colors are typically stored as 32-bit numbers. Each channel uses 8 bits. And if you look at binary in a calculator, 2 for binary to the 8th power, meaning 8 bits, is 256. And that gives us a maximum of 255 because computers count from 0 instead of 1. So the range from 0 up till 255 has 256 different combinations. So this number 255, if it were represented in binary, would be 8 ones. Now that gets cumbersome, so the alternative is this hexadecimal notation. So the hashtag just means that it's a color. The FF is the red channel, and it's equivalent to the 8 ones. The next 00 is the green channel, and the last 00 is the blue channel. And I mentioned that colors are 32 bits. Since red, green, and blue are each 8 bits, 8 times 3 is actually only 24. So if I add 8 more, it becomes the 32. The final 8 bits are for the alpha channel. The alpha channel is for transparency. So if I look at a screen for a video game, you'll notice that the game is rendered in layers. You have the background, which is underneath everything, which is this landscape that the characters are walking on. And on top of that is rendered the 3D model of the character. And on top of that is rendered any UI elements like this damage number, this health number, this health bar, or the heads-up display that gives the player information about the game. You can see how they're all rendered in layers. The transparency is necessary so that it can blend the images together. For example, on this number 160, you can see that the 0 is hollow. It's transparent on the center so that it blends with the background and you can still see the background bleeding through underneath. So transparency is very useful when you're rendering graphics, but since we're taking the final rendered image and analyzing it, we don't need transparency. So we're just going to be using 24-bit colors. So that's how an individual pixel is represented, and an image is just a grid of pixels. So in this case, 2 pixels wide and 3 pixels tall. So if I opened up Paint and changed it to 2 wide and 3 tall, then I could draw these red pixels. So I have 1 pixel on the top left corner, 1 on the top right, here's my second row, and here's my third row. So that's my example image, which is being represented here. So this second image would be almost identical, except the intensity of the red would be very slightly less. And this third image, instead of being red, it's going to be green. So if we open up Color Cop, we can see how the colors mix together. For example, if I take full intensity red and mix it with full intensity blue, I get kind of a purplish color. But if I reduce the amount of blue, then it's a bit more pink. But if instead I have full blue and reduce the red, it's a bit more blue. So how am I going to determine if these two images are similar? If I just wanted to know if they were identical, I could compare each pixel one at a time, and within the pixel I could compare the intensity of each channel, red, green, and blue. The problem with that is it's going to be rare for images to truly be identical. For example, in a game, you may have glowing effects where an icon shimmers or shines for a second to catch the user's attention. And so if I take two different screenshots that are a second apart, they may not be identical, but they should still be similar. And also, different hardware may render graphics slightly differently. For example, really old hardware would not support 32-bit color, and gamers play at different resolutions. So that's why we have this threshold parameter, is to define what percentage of similarity we want to consider close enough. And that's going to depend on our specific use case and what we're trying to accomplish. So the way the mean squared error algorithm works is images that are pretty similar, like 1 and 2, it will calculate a very small result. And images that are very different, like image 3, it will calculate a very large result. So that way we can easily distinguish between images that are almost the same compared to images that are totally different. And the way it does that is first it calculates the error, which is going to be each channel and each pixel just subtracting the numbers to get the difference between them, the delta. So for comparing images 1 and 2, the error would be a brand new image that has 1s for the red channel and 0s for the green and blue, because 255 and 254 are 1 off from each other. Next, it's going to square them. So this would be the squared error. So 0 times 0 is still 0, and 1 times 1 is still 1. So in this case, the squared error is the same as the original error. But let's just pretend for a minute that this number was 250 instead of 254. That would make our error be 4, and our squared error would be 16, because 4 times 4 is 16. So you'll notice that only making them off by 3 additional values actually made the squared value go up a lot. So that's the benefit of squaring it, is numbers that are similar stay low, but numbers that are far away get really big. So finally, we're going to get the average, or the mean, by adding up all of these numbers together and dividing by the count. So I have 6 total pixels, and each pixel has 3 numbers. So that means I have a total of 18 numbers. And I'm going to add 16 and 0 and 0 and 16 and 0 and 0. So if I add up all of these 18 numbers, I get a total of 96. And then when I divide it by 18, I get 5.3. So that is the mean or average squared error. Finally, I want to convert this to a percentage. So if I consider the highest possible mean squared error, which would be essentially if I compared an image with all zeros or black to an image of all 255s or white, my mean squared error would become 256 times 256. So I'm going to divide this 5.3 by this number to get a percentage of how different they are. So I'll get a number between 1% and 100%. So in this case, it is extremely small. And so I could have a very small threshold and consider those numbers similar. So let's compare image 3 to image 1 to see how different our result is. So in this case, the error for the red channel is 255, the green is 0, and the blue is an additional 255. So for our squared error, the red would be 255 times 255, the green would be 0, and the blue would also be 255 times 255. So you can see how that would be a very large number. And then after that's averaged, it becomes 43,350. So to convert that to a percentage, we would divide it by that same normalization factor of 255 times 255, and we get 0.6, meaning 60%. But if we compare that to our previous result with the very similar images, 5.3 divided by our normalization factor gives us 0.00008. So that's not even 1%. So you can see very similar images get a very small number very different images get a very large number. Now, 0.6 doesn't sound like a large number, but the maximum is 1, meaning 100%. Hopefully that made sense. Let's code this up. So I'm going to start by taking image A and calling the absdiff function, which is part of the OpenCV library, and pass it the image B. This stands for absolute value difference. So the difference is going to subtract the channels from each other, red minus red from each pixel, green minus green from each pixel, etc. And the absolute value will convert all negative numbers to positive. The reason for the absolute value is so that the order the images are subtracted from each other doesn't matter. Because if you consider that the first image maybe has 5 for its red and the second has 4 for its red, if you swapped the order 4 minus 5, you're going to get a negative 1 instead of a positive 1. So the purpose of the absolute value is to make sure that the result is the same regardless of which order you subtract. Next, I need to square the difference, but unfortunately OpenCV does not have a method for that, but TensorFlow does. So I'm going to call CV to tensor on this diffed image. And I coded that up in the last video where we did OCR, or text recognition. So you can go back to that video if you need the code for this method. But just know it's just converting from OpenCV matrix format to TensorFlow matrix format so that we have access to the TensorFlow APIs. So now that it's a tensor, I have access to the square method. And after I square it, I can do the average. So now we have our mean squared error in our result variable. However, it's not normalized to a percentage from 1 to 100. So to do that, I'm going to take my result variable, and it's still inside of a tensor, which is a matrix, even though it only has one value inside of it. So I'm going to call the .data function to convert it from a tensor to just a normal JavaScript number. The data method has an asynchronous version and a synchronous version. This is because if you're dealing with a really large matrix, the math that we executed earlier, the square and the mean, could take a long time. And the way TensorFlow works is the commands you send it are queued up in a chain, and they don't actually execute until you extract the final value. So I'm going to call the synchronous version just so it keeps our code simple. I explained asynchronous code with promises or the await command in the last video, and you could use that method as well. So the data sync method will give me the matrix as a JavaScript variable, and it's going to think that it's an array because that's what matrices are. But because I did the average, I know I only have one single value. So this is one example where TypeScript gets confused. So I'm going to cast it to the any type and then immediately afterwards cast it to the number type to correct that bug in the TypeScript compiler. It's probably not really TypeScript's fault. It's probably whoever made the type definitions for TensorFlow didn't label this method correctly. As you can see, it says that it returns an array, but it could technically also return a number. Now that I have the number, I'm going to divide it by our maximum error, which is 255 times 255. So that will give us a percentage from 1 to 100. So I'll call that a normalized result. And then since I wanted a true or false, I'll just return this value compared to my threshold. So as long as this value is smaller than my threshold, I will consider it similar, which will be true. I'll return false if it's greater than the threshold because that means they are not similar. Okay, that's all we need for this function. I'm going to put a breakpoint on this comparison because the first time I test this, I want to see what kind of percentage I get for a matching image so I know what value to use as a threshold. So let's test out this function. So inside this test code, I'm just going to call our image is similar, and I need to pass it two different images. And for the threshold, since I don't know what to put, I'll just start it at 0. So the images I want to compare, I'm going to take this blue streak image and I'm going to look for this blue fire as well as red fire at these screen coordinates. So because I'm going to need to crop this image to get the correct locations, I'm just going to put my mouse on the top left corner of the icon, and on the bottom left corner of my screen, you'll see the X and Y coordinates within the image. Then I'm going to draw a box around it, and that gives me the width and height as well. So to read that image, I'll use the OpenCV imRead command, and I'll paste in the path to my image. And I need to tell OpenCV what mode to read the image in. So I'm going to specify that I want color. because some computer vision algorithms don't need the color and they work off of grayscale. Next, I'm going to take the blue streak and red streak icons and load them up as well. Blue streak equals IamRead, paste in the path and use color. Same for the red streak. I'm going to move this comparison image to a variable called game image, and I will crop it before I compare if they're similar. So let me call crop image, and this method I coded in the last video about Tesseract optical character recognition, so you can review that video for how that's coded. I'll take my game image and the coordinates I found in Paint. So now my game screen has been cropped to just the correct coordinates, and I'll compare that to the blue streak image. Okay, I can execute this with the npx command, ts-node./index.ts. npx is npm execute, ts is TypeScript, so it first will compile from TypeScript to JavaScript, and then it will use node to execute the file. And actually, rather than adding a breakpoint here, I'll just log whatever the result was from running my calculation. So I've got my two comparison icons. I have the blue streak icon and the red streak icon. And then for images, I have a board game with a blue streak on it. And then for in-game screenshots, I have one with a blue streak, which I can crop to compare. And I have one with a red streak, which I can crop to compare. And then I could take an image that's not the main board screen, so that if it crops that same section, it will get something completely unrelated. And we can use that to see how well our algorithm works. So I have my two icons loaded into variables. For my game screens, I've got one example which should have a blue icon, one example that should have a red icon, and one example which should be completely unrelated. Let's try first with the blue game screenshot against the blue icon and see what kind of result we get. Run it. I got 16% match. Now, that seems a bit worse than I would expect. However, if I look at my comparison icon and I compare it to the in-game screen, when I crop, I'm cropping a square, even though the icon is round. And so it's actually comparing the background around the icon, which I would prefer to exclude. So I could improve this algorithm by taking my comparison icon, changing all the white to transparent, and then changing my mean squared error to ignore any pixels that are transparent, because the difference it's giving me is probably the fact that the background is purple and it's comparing that purple to the white, because the rest of the icons should be the same. And that could be different for every game of TFT because the background is a skin that the player selects. So that alpha could be important. Now, I'm not going to code that right now. The reason why is there is a different image comparison algorithm that solves some of these issues that mean squared error has. So I'll leave that for an exercise for you if you want to use mean squared error to code that piece to ignore the transparent pixels in your source image. But let's just verify that in general this is working. So now I got 16%. If I instead compare it to the red icon, so my game image is the screen with a blue icon and a purple background, and I'm comparing it with a red icon and a white background. Hopefully I should get higher than 16%. Okay, 18. So it is a worse match. So in both cases, it seems to be indicating that there is a fire icon there. And if I wanted to know whether it's blue or red, I should just compare against both, and whichever value is smaller is the one I should keep, because it is a closer match to the blue than it was to the red. Now let's compare it to this carousel image, which should be completely different, and hopefully we get a very high number, meaning that it's not similar at all. Run it. Okay, 0.34. So it got to about double. So if I were to give a default value to this threshold, I was just passing in 0. Maybe I'd say something like anything 0.2 or lower is considered similar, and anything higher than 0.2 is not. But whichever one gives a better threshold between the blue and the red is the one I want to keep. If I coded the transparency portion, I would expect instead of 16 and 18, I should get very close to 0. So that would be an important way to improve this code. The reason I'm not going to code that is this was just to demonstrate the basics of image comparison, and I'm going to show a much better algorithm in a second. So the issue with that comparison, mean squared error, is not only do I have to deal with background issues, but also if there's any kind of effect, for example, if this icon was glowing to get the user's attention, some kind of animation, that would also affect it. Also screen resolution and possibly differences in hardware. And so even though it can work, it's temperamental. And most importantly, it requires that we know the exact X and Y coordinates on the screen. But I mentioned previously that with this carousel screen, we're still wanting to search for an icon, but that icon is moving around the screen. We don't know the coordinates. So let's code up a separate function to help us search for an image. I'm going to modify this test code slightly. I'm going to keep the carousel, and I'm not going to crop it yet, but I'll remove these other two game images. And instead of the blue and red streak, I'm going to get two items. So if I look at the carousel screenshot, I see, for example, here an item called Tear of the Goddess. So here I have a copy of all of the icons, and I'm just going to load this Tear of the Goddess icon into a variable. So paste in the path, rename it to Tear. Now, whenever you're testing your code, you want to have one example that you know is going to work and one example that you know is going to fail, so that you can try both scenarios and make sure it really does work and fail to prove that your code is really working. So for my bad example, I'll just look at this carousel and I'll pick any item that's not shown here. If I look at this item, blue buff, it is not in this screenshot anywhere, but it's a good example to compare against Tear because they both have a lot of blue. So I want to see if this algorithm can distinguish between the two. So I'll put this blue buff into a variable. Okay, I've pasted the path in and renamed my variable. So instead of checking if images are similar, instead I want to code a new method called search for image locations. This function will take a template, which will be my Tear of the Goddess or blue buff item, and that will be a computer vision matrix or an image. And I want to search for that in a background image, which will also be a computer vision matrix. And again, I want some kind of threshold, but I don't know what value I'll use yet. And I want it to return an array of rectangles. So a rectangle will have an X and a Y coordinate for the top left corner, and then it'll have a width and a height. So that will tell me the exact square that it found that image. So this method is actually quite simple because OpenCV has a built-in method for this. It's called the match template function. And I call it from my background image, I pass in my template image, and I tell it which algorithm to use. You can experiment with these different algorithms to see which works the best, but I prefer the squared diffed normed. Compared to the other ones, this one seems the fastest, and it seems equally accurate compared to the others. Now, I'm not going to go into depth on how this method works, but if you want to Google it, the term is called a fast Fourier transform, or FFT, and it comes from a French mathematician, and you would study it in a linear algebra class. But it's a complex math formula on matrices that, in our case, helps us search images. So I'm going to put the results of this function into a variable, and the result is a matrix, which we could think of as an image, but it's not an image you would typically look at. Instead, it's the calculation at each pixel of how likely that pixel is to be the location of this template. For example, let's say I had an image like this. If my template was this teal puzzle piece, like this, then the resulting matrix would be something like this, where the top left corner is a 100% match, and all three of the other corners are a 0% match. However, we have to remember that these are pixels. So if we show grid lines here, each of these squares is a pixel. So in reality, the top left pixel would be a 100% match, but the center of this teal would only be probably a 50% match, because it's telling you how likely the template is to start at that location. And so if it started in the middle of this teal, then the teal would bleed down into the red and bleed over into the orange. And so after we run the fast Fourier transform, we can scan the matrix for a cluster of really large numbers and use that to make a good guess as to the location of our search image. And once we've determined that, we can use the mean squared error algorithm that we coded previously to double check that we really found the correct image. So the benefit to the fast Fourier transform is in its name. It's very fast, because think about if we were to use the mean squared error algorithm to search this entire image for this teal image. What it would have to do to search for this teal puzzle piece in this entire image, if it doesn't know the location ahead of time, is it would have to check every possible location and run the mean squared error. So for example, it would run one time with this top left coordinate, then it would run again with this next coordinate over, and then a third time with this next coordinate. So if you think about the size of the grid, you've got hundreds of coordinates you would have to check. So if each individual mean squared error algorithm takes a second and you have to run hundreds of times, it's going to take way too long. In fact, if you think about a 4K image, which is fairly standard nowadays for gaming, you have 3840 wide by 2160 tall. That's the number of pixels in a 4K image. So you would have to run the mean squared error algorithm 8 million times to search one image. Now, computers are fast, but running a calculation 8 million times is probably going to be slow. I tested the mean squared error algorithm, and on my machine, which is a top of the line fast computer today, it takes 200 microseconds or 0.2 of a millisecond to run a single mean squared error check. And it gets worse because not only would we have to do 8 million times for a single 4K image, that's for each image that we're searching for. So on this carousel screen, there are multiple icons. If I search for the Tear of the Goddess icon 8 million times, I'll only find just this one. Separately, I have to search for the Giant's Belt 8 million times. And separately, I have to search for the recurve bow 8 million times. And there are 54 different items to search for. And because these items are moving around in real time, if I want my character to move to pick up the item, I have to keep searching again to know their new location as they're moving to keep my trajectory. So it's just not feasible. If you were to take the 8 million searches times the 54 items, and that's 200 microseconds each, there are 1 million microseconds in a second. So that would be 90,000 seconds. There are 3,600 seconds in an hour. So that would mean it would take 24 hours to search this carousel image if it's in 4K for 54 different items. Now, obviously that's not going to work. The game's going to be over in 20 minutes and the screen's going to be over in 10 seconds. We can't take 24 hours to analyze the image. So there are little micro optimizations we could do. For example, rather than searching this entire image, we could crop it to just the center section, and that would help. And in addition, instead of searching the image in 4K, we could scale it down small to do the search. And then once we think we found the correct location, we could scale it up big again and do a double check just on the exact coordinates we found. But those type of micro optimizations, they might speed it up from maybe 24 hours up to maybe 1 hour, but that's still not going to be good enough. In that situation, we really just need a brand new algorithm. And that's why we're going to use the fast Fourier transform. And another benefit to FFT is it also is more resilient to minor changes in the image. So if the image has been rotated slightly, if it has a small shader effect like a glow, as long as it's still pretty close to the image we're searching for, it should still find a match. So as I mentioned before, this would be how the fast Fourier transform results would look, except that in our example, each puzzle piece isn't one single pixel, it's actually a lot of pixels. So instead of looking like this, it would actually be something like this, where the top left pixel is a 100% match, the pixels around it are a 90% match, the pixels around those are an 80% match. So as my cursor gets further away from the correct position for the teal puzzle piece, it's less and less of a match. Another way you could visualize this is on the carousel screen, after running the fast Fourier transform, if I search for an icon that does not exist anywhere, the carousel screen kind of turns to grayscale, but there's no obvious indicator of where this icon exists because it couldn't find it. It should turn black when it finds it, and the darkest we get is kind of a gray. And it doesn't really look like the carousel screen anymore, but you can see a vague resemblance. Whereas if I search for an icon that does exist, you'll notice there's a distinct black spot on the image where it was found. And as I mentioned, we want to search for kind of a cluster of black dots all next to each other, because if there are a lot of pixels close to each other that all have a high match percentage, that's a good indicator that it found the image. Whereas if you just had a single black pixel by itself, that's not a strong indicator. And ideally, the size of the cluster of black pixels should be roughly the size of the search image that you're looking for. So that's how this match template function works. And what's really cool about it is when I tested with a cropped version of the carousel, so just analyzing this center section, it was able to search for a single image in about 80 milliseconds. And if we're searching for 54 different icons, that's 4,000 milliseconds. Well, there are 1,000 milliseconds in a second. So that's essentially 4 seconds. So we're getting from 1 hour as the best case scenario in the other algorithm down to 4 seconds with this algorithm. And it would be better if it could be less than 4 seconds, but I think that's fast enough that the AI could make a decision. And we could probably do some micro optimizations to make it a little faster if we needed to. The easiest would probably be, nowadays computers have multiple cores. On my PC, I've got 16 different cores. Each of these can run a different method at the same time. So since I have 54 images I'm searching for, I can let each core search just 4 of the images, then all 16 cores will be fully active at the same time, multitasking. And so then instead of 4 seconds, it should only be 1/4 of a second because I can divide it by 16 cores. And that would be plenty fast. So let's finish coding this up. Now that OpenCV has given me the results, I just need to search for an area with black pixels, and then afterwards double check those locations with the mean squared error. Because although mean squared error is slow when you're running it across millions of locations, since this will narrow it down to very few locations, it should be fast to just check those few locations. In order to iterate through my matrix, I'm just going to make 2 for loops that are nested. The outer loop will iterate over the columns, and the inner loop will iterate over the rows of the image. So I'll use variables x and y. This means in this inner line of code, the variable x and y will be the exact pixel of the image I'm looking at, and it will run for a 4K image 8 million times, 1 over each different pixel in the image. And that's okay, even though it's iterating a lot of times, because these types of programming commands are very fast, and the computer can handle checking a single pixel 8 million times. It's running the mean squared error 8 million times that would be an issue, because mean squared error is doing a lot of really complex math. So to check the value at the current pixel, I can use the at function on the OpenCV matrix, and I'll pass in my coordinates. So that's my current value. And then I'm going to check if it's smaller than my threshold. And if so, I'll consider it a possible match. So I'll make an array of all my possible matches. And if the value is less than my threshold, I'll push a new value onto the array for that possible match. Now remember, I'm using the rectangle structure, which has an x and a y coordinate, as well as a width and a height. So I'll make a new object with x and y, as well as width, which is my search template's width, and height, which is my search template's height. And because it's a matrix, not an image, then it uses the terms rows and columns instead of width and height. And OpenCV uses the terms columns and rows instead of width and height. And finally, I'm going to pass my value, which is the percent match. So now that I have a list of which coordinates I want to consider, I'll loop over these possible matches and check for a cluster of possible matches that are close together by combining a cluster into one single match. So the way I'll consolidate this cluster of black pixels into one single match is by removing the duplicate gray pixels that are around it. So if I zoom in to these black pixels, and remember this is a matrix and I don't know without doing some math which point is the darkest, what I can do is sort by the darkest pixels, which would give me this spot in the center. And if I know that this sort icon that I was searching for is 50 pixels wide by 50 pixels tall, then after finding the darkest pixel, I can draw a 50 by 50 square around it and say any pixels within here that have a smaller value can be removed as duplicates. That way, if I have 2 different dark spots, I can consider them both to be a match. But if the dark spot contains 100 black pixels, I can just keep the best match within those 100 pixels instead of checking every one of them. And then after I've narrowed it down to just the darkest pixel within each cluster, then I can run the mean squared error on each of those as a final check that I've really found the correct spot. So to do that, first I'm going to sort my possible matches using the order by function of Lodash. And I'm going to sort by the value, which is the percentage match. And remember, we were checking for values less than the threshold. So that means the smaller the value, the closer it is of a match. For example, 0 is black, which is a close match. 1 is white, which is not a close match. And this is sorting ascending. So the black pixels will be at the beginning of my array, and the white pixels will be at the end of my array. And I've already narrowed it down to just values under my threshold. So I'm not considering that many pixels anymore. I'm really only considering the black and dark gray. Now that it's sorted, I'm going to make an array to store the duplicates, and I'm going to loop over each of my possible matches, and I'll call the variable A because I want to do an A-B comparison between two different pixels to see if there are any gray pixels that are within the boundary of a black pixel, because then those gray pixels can be removed. So the B values will be the gray pixels. And the reason I know that is since I've sorted, the first elements in my array are the darkest. So A is going to start at the darkest pixel and it's going to loop over the entire array. But B, I'll have it start at A plus 1. So it's only comparing pixels that are less dark. So I'll put the first match I'm comparing into a match A variable and the second one into a match B variable. And since I already know that B is not as dark, then if it's within the same region as the first pixel, I'll consider it a duplicate. And the size of the region will be the size of the search image or template. So that's basically the size of the item I'm searching for. So to do that, I'll subtract the coordinate from each pixel and see if the distance of how far away the pixels are is less than the width of my search image. That would mean they're close enough together to be considered the same region, and so they're a duplicate. And I'll do a math.absolute value on that subtraction so that the order of which coordinate is subtracted first doesn't matter. So I don't have to consider negative values. And I'll do the same thing with the height. So if the second pixel, which is not as dark, is both within the same vertical and horizontal region as the first pixel, which is darker, I will consider the second pixel to be a duplicate by pushing that match into the duplicate array. So now that I have a list of all the duplicates, I can get my final set of matches by using the Lodash difference function, which uses set logic on two arrays to remove any values from the first array which exist in the second array. So my initial array is all of my matches, and I'm removing any values that are in my duplicate array. Now that I've removed all of the duplicates, I need to double check with the mean squared error to remove any matches that were incorrect. So I'll put these into the verified matches variable, and I'll return it at the end of my search function. And all I need to do to test each of these matches is to call the filter function. Now, filter comes from functional programming, so it will loop over every element in the array and pass each element to an inner function. The parameter to the inner function will be the element of the array that I'm currently looping over. And after the arrow comes the body of the function. This function needs to return true or false based on if I want to keep that value in the final array. So I'm going to call the rImagesSimilar function that I previously coded. And since that gives me true or false, if I return that, it will only keep the matches where mean squared error says the images are similar. So I'm using fast Fourier transform to do the initial search, which is mostly accurate, but it's also fast. And then I'm double checking those results with mean squared error, which is more accurate, but is not designed to search a large image. It's only designed to compare two images. So in order to call this function, I first need to crop my carousel to the right coordinates. So the background image, which was passed in to my function, is the carousel image I'm searching, and the crop location is the current match that I'm looking at. So I have match.x, match.y, match.width, and match.height. Now that I have my cropped image, I can compare it to my original template, which is the item icon I was searching for. And then we need the threshold value. So as we discussed before with this our image is similar, we needed to use a 0.2 for it to work because I was looking at an icon that had transparency in its border and the background that was bleeding through was causing a poor match. But all of my items are square, none of them have transparency. So that won't be an issue. And because of that, I can actually use probably a 4% similarity threshold because it'll be a much closer match. The value can be much smaller. Now, I'll need to do testing with this match template function to determine what threshold works well for it because it's a different algorithm than mean squared error. So it may be in a completely different range. And the issue with that is I have a threshold being passed into search image location, but I need to also pass a threshold into our image is similar. But because they use different algorithms, their threshold is going to be at a different scale. Anytime you're comparing values of two different algorithms that have a different scale, you need to normalize the values to convert them to be the same scale. So I've already done testing with this. I already know that if I use the same 4% threshold that mean squared error needs, then it will not work with the fast Fourier transform because the threshold will be too low. So I'm going to normalize it by pasting in a constant variable. Now, the value I found that works best is about 0.25, but I'm putting it into a constant variable so that it's easy to modify in the future as needed. And I'll just take the threshold that's passed into my function and divide by this ratio to get a threshold that works well. So for example, 0.04 divided by 0.25 gives us 0.16. And I found that with the fast Fourier transform and square diff normed algorithm, 0.16 seems to work well in my case of searching for items on the carousel. Now I can pass the threshold into the our image is similar, and this code should be done. So let's execute our test function. We've got our carousel image, and we're going to pass that to the search for image locations as the background that we're searching within. And then we'll pass in Tear of the Goddess as the template we're searching for, which I expect it to find. Afterwards, we'll test with blue buff, which it should not be able to find. And I'll put the result into an image locations variable, and I'll output that to the console so that we can see how it worked. JSON.stringify takes a JavaScript variable and converts it to JSON format. And JSON is designed to be both human and machine readable, so it's useful for logging messages, in particular when you have values that are complex. So in our case, image location is an array, but inside the array are rectangle objects which have an X, Y, width, and height. So this allows me to print all of that to the screen really easily for debugging. So let's open up the console and run our code. Okay, I got an error, index out of bounds, calling the at function on a computer vision matrix variable. I realized the mistake I made here. CV wants the Y value passed in first and the X value passed in second. That was my mistake. Okay, now that we've got that error fixed, let's try one more time. Okay, we're not getting an exception, but it's not finding the image anywhere. So let's see what mistake I made. I mentioned earlier that fast Fourier transform can handle slight discrepancies as far as if the image you're searching for is slightly rotated or if it has a minor shader effect, like a minor glow. But we still want to minimize them as much as possible because we will need to increase our threshold the more effects there are that are making our images not match. And in this case, there are not any effects. However, the images are not scaled quite the same. So if I were to highlight this icon, you can see it's around 30 pixels wide and tall. But the items I have here, for example, Tear of the Goddess, when I open it, it's 64 by 64. So the icon file I have is of higher quality and larger than what's being rendered on the screen. So I think if I resize my icons to match the size on the carousel, it will work better. So OpenCV has a resize method. So I'm just going to pass in 32 and 32 to match the carousel. And I'll do that both on Tear of the Goddess and on blue buff. And I think that will work better. Let's try. Okay, perfect. So this gave me only one coordinate where it says it found the Tear of the Goddess, which is 859 and 553. So let's open up our carousel. And as I move the mouse around, the bottom left corner of the screen here should show the coordinate I'm at. So if I go to the top left corner of Tear of the Goddess, I get let's see, 856, 551, 859, 553. So that's spot on. It was off by a couple, but I think that was me not holding the mouse in the correct position. I think the code did perfectly. And you'll notice here the value 0.06. So it gave a quite low threshold, which is great. Now that seems wrong because I said it has to be 0.04 or smaller. It's actually fine. The reason is I normalized the value when I compared it, but I did not normalize it when I stored it into my match results. So that's a little bug I could fix, but it doesn't really matter. It's just a debugging thing. It doesn't affect my results. So let's try it now with blue buff. In this case, I hope it does not find any image at all because it should not be on the carousel screen. Okay, perfect. It didn't. Now I am curious if I didn't run this double check with the verified matches. I wonder, because they both have a lot of blue in them, if it might still return it. I don't know if it will or not, but I'll just comment out this section temporarily and just return the matches without verifying them, just out of curiosity. Okay, even then, that's really great news. So that shows that with the fast Fourier transform, even though blue buff has quite a bit of blue like the Tear of the Goddess has, they're different enough that the fast Fourier transform does not get confused. And I think that's because the Fourier transform is actually able to recognize shapes and intensities as well. So I'd say the intensity of the colors are quite similar, but the shapes are very different. And the blue buff also has kind of this brownish stuff on the edges. So it's good to know that I didn't need to verify the matches, but it doesn't slow down the result much. And I think it's nice to just double check it. So another place the fast Fourier transform might be useful would be for searching for these blue question marks, because they get dropped in random spots on the screen whenever you kill minions, and you need to right click on them in order to open them up, and they give you a random bonus. So I don't need to code anything additional there. If I wanted to do that, I would simply change from the carousel screen to this blue item drop image, and then instead of this Tear of the Goddess PNG, I would pass in this TFT game blue item drop image. Now this would have the similar issue as the blue and red fire before, where I would want to make sure I excluded the alpha channel around it when doing the comparison, but otherwise it should work fine. So that's the beauty of these two functions we've written, is they're generic. They can be used for any part of the game as long as you give it the correct template image and image that you want to search. So between this and the Tesseract OCR that I demonstrated in a previous video, we can extract virtually anything that we need to out of the game while it's being played. So now that we have that, we can send it into our AI model to ask it what decision we should make each round. Let me know in the comments below if you have any questions about computer vision techniques. In future videos, I plan to cover how I'm gathering match history from online TFT games that I can use to train an AI model with, as well as how to use neural networks to take all the complicated statistics in TFT and analyze them to determine which decision is best to make during any given game state. And finally, how to remote control the computer to simulate keyboard and mouse instructions as if it were a human, so the game can play itself. Hopefully those topics are interesting to you. If there's other topics you'd like to learn about, let me know in the comments below. Stay tuned for future videos, and thanks for watching.